Hello, today we are going to look at how to represent functions using power series, various types of functions using power series. So let's go back to what we talked about a little bit yesterday and what a power series actually is. So if you remember, the definition of a power series says that a power series is some sigma from n to infinity of a function a sub n times x minus c raised to the n power, where we're centered at c, and we have something in this form where this a sub n that's written right here is really just a series, or a sequence rather, of constants. It's our coefficients. So this is what a power series looks like. And our goal is to transform some functions that maybe we can't do a whole lot with algebraically, like taking antiderivatives or derivative work. Usually just antiderivatives are the problem. But how do we change them into a polynomial? How do we change them into what we call a power series? So what we're going to focus on first is what it looks like when the power series begin as a rational function and how we can write them in the form of a geometric series, a over 1 minus r. Okay, so based on what we know about geometric series. So let's go back to the idea of a geometric series. We know that a geometric series takes this form from n equals 0 to infinity of maybe there's an a in front, a times r to the n power. And we know that it converges to this sum, this infinite sum, if what is true. What has to be true in order to make a power series converge? Well, we talked about this a little bit yesterday as well, and that is that the absolute value of r, that common ratio, needs to be less than 1. And we looked at that yesterday when we talked about looking for our interval of convergence for a power series. So we're looking at that. Now, what I'm hoping to do is to turn a function, something like this first example that says f of x equals 3 over 1 minus x to the fourth. It's centered at x equals 0. And my goal is to write a power series that looks similar to the one up above. And we're going to start with the idea of a geometric series. So our goal for this is to try to get this into the form, is to make it get into form of, we want it in this form, 1 over 1 minus r. That's my goal. That's how I'm going to start all of these problems. Now, maybe I have a coefficient multiplied by it, but our goal is to be 1 over 1 minus r. So if we take the function that was given, the function that was given was f of x equals 3 over 1 minus x to the fourth, ours might look like this. If we pull out the constant 3, and then I would have 1 over 1 minus, and then this x to the fourth would be my common ratio here. So this is the common ratio that we're talking about. This is that r value that we're looking for. Okay, so a little strange. We're really just rewriting this one, and it obviously will get a little bit more complicated. But if we can do this, then I can say that my function is going to be equivalent to 3 times the series from n equals 0 to infinity of, and this is where we go back to that r value that we just found, and I'm going to raise our r to the n power. Well, the r that I have, is this x to the fourth. So I've got this x to the fourth that I'm going to raise to the n power. Now at this point, I'm going to simplify this just a little bit. If I combine like terms, maybe I move that 3 on the inside, it doesn't really matter. Another way that you could see this series is that this is from n equals 0 to infinity of 3 times x raised to the 4n power. Great. Okay, And what we're saying is that this is equivalent to the function of 3 over 1 minus x to the fourth. Great, especially if I need to try to integrate this. This makes it a little bit easier to deal with. Now, one of the things it talks about is the interval of convergence. This is what we also worked on yesterday. Remember, for my interval, we need to remember that r, the absolute value of r, needs to be less than 1 in order for this to converge. In order for a geometric series to converge, meaning in order for us to be able to find a sum, that absolute value of the r needs to be less than 1. Well, we said that the r value was this x to the fourth power. This is my r value, and so I know that this expression needs to be less than 1, the absolute value of it. Well, if the absolute value of x to the fourth needs to be less than 1, then we know that the absolute value, if I take the fourth root of both of these, of x needs to be less than 1, which means that x would need to fall between 1 and negative 1. Okay, I'm going to write this down, but just so that you have it, we don't need to test the endpoints. So yesterday, we tested the endpoints for our intervals of convergence, and we don't need to do that here because we know a geometric series will diverge when r is 1. So if the r value is 1, it diverges. So we don't need to test the endpoints for a geometric series, which is what we're working with. So this is my answer to the problem. This is me putting or rewriting the function f of x equals 3 over 1 minus x to the fourth as a power series representation. Okay, well, I wish I could say they're all going to be wonderful and nice and easy like that. We know that's not true. Every now and again, we get some that are a little bit more complicated. We're going to do some on here that we just really won't see very often, but I think it would be good to present just in case they do come up. So let's look at example 2. We're going to try example 2 similar to how we did example 1. There's a bit more algebra manipulation that needs to happen, but I'm also going to show you how we can do this using another method. So my goal is to find a power series representation for this function f of x equals 6 over x plus 2. Now, if you remember, my goal is to get it into this form. I want it to be 1 over 1 minus r. That's my goal. And at the moment, this looks nothing like that. So let's start with the fact that I could pull out a 6. That 6 I could get rid of. So we would have that this is 6 times 1 over 2 plus x. You'll notice I switched the order in the denominator. Instead of saying x plus 2, I put 2 plus x. And the reason I did that is because if my goal is to get some constant here, specifically 1, minus a common ratio here, I need it in that order. So I'm just going to adjust the order. Notice I haven't changed my signs any. It's still the same thing. I'm just rewriting it. Okay, here's where it gets a little weird. I want a 1. My goal is to make this a 1. And so how I'm going to do that, I still have the 6 that's out front. What I'm going to do now in the denominator is factor out a 2, which will leave me with 1 plus x over 2. Great. So I'm a little bit closer, except that my goal is to get it to be 1 minus r, and right now I have 1 plus an r. So one more step that I'm going to have to take for this is I'm going to write this as 6 times 1 over 2 times 1 minus negative x over 2. Okay, a little bit silly to do that, but it's going to put it into the correct form. The next thing that I can actually do is simplify. I have a 6 and a divided by 2, so I'm going to go ahead and just simplify that to be 3 times 1 over 1 minus negative x over 2. Now I have it in the right form of 1 over 1 minus r. That's the form I want. So we can say that f of x, which we know is 6 over x plus 2, could actually be written as the series from n equals 0 to infinity of 3 times the r value, negative x over 2 to the n power. Okay, here's the problem with this one and the way it's written. I see that in my parentheses, I have a negative. Now, this isn't wrong. It is correct, but oftentimes with that negative, and I'm raising it to an n power, we won't actually see it written that way. We know that a negative to the n power means alternating. So oftentimes what will happen is we will see this alternating part pulled out and maybe even all the way in front of the 3. But we have the alternating part times 3 raised to the x over 2 to the n power. This is more common to what you might see. It doesn't mean that this answer is incorrect. This is 100% correct. But just be aware that if I've got a negative that I'm raising to the n power, it means it's alternating. This is an alternating series. Okay, does that change anything when we go to speak about my interval of convergence? We know this is the series, and you could choose either one of these would be acceptable for the series. But what about my my interval part? What does that look like? Well, if we talk about our interval, we know our interval has to be the absolute value of r, which we said was the negative x over 2. So we have that value here. And I know that this value needs to be less than 1. Okay, well, it's absolute value. And so I'm going to go ahead and get rid of the absolute value or the negative by taking the absolute value. So we would get that the absolute value of x over 2 is less than 1. And then I'm going to go ahead and multiply by the 2, so I get the absolute value of x is less than 2, which means that my interval of convergence goes from -2 to 2. Again, we don't need to test the endpoints because it was a geometric series. That was our whole goal. Now, it is also possible to find a power series other ways. Maybe you don't recognize it's geometric. Maybe you just want to try a different method. And so if that's the case, one of the methods that we can use is the idea of long division. I know that's not everybody's favorite idea, and this is going to get a little bit weird because we're dividing two very random things together. So I'm going to take and I'm going to divide 6 by 2 plus x. Okay, well, if you remember how long division works, our goal is to take this first term and divide it or see how many times it goes into this first term here. And it happens to go in 3 times. So if we take 3 and we multiply it by 2 and by x, we would get 6 and we would get positive 3x. And remember what we do then is we go in and we change both of the signs. So this will become negative and this will become negative. And so as I bring down my terms, I'm hoping to get 2 to go into negative, oops, I lost my x, negative 3x. My goal is to get 2 to divide into negative 3x. Okay, well, if 2 is going to divide into negative 3x, it's going to go in negative 3 over 2x times. That way, when I multiply negative 3 over 2x times 2, we get negative 3x. Now I'm going to change, I need to finish multiplying. I'm going to multiply then the negative 3 over 2x times x, which is going to give me negative 3 over 2x squared. And I'm going to go through and change both of these signs. And then I'm going to combine them together. This is going to leave me with 3 over 2x squared. And hopefully you start to see the pattern. Now I'm going to see 2. How many times does 2 divide into 3 over 2x squared? And that goes in positive 3 over 4x squared. So that if I were to multiply 3 over 4x squared by 2, we'd get 3 over 2x squared plus 3 over 4x cubed, and we would keep this pattern going. And you can see that the way we divide this is just going to go on for an infinite number of times. We're just going to keep dividing and dividing. So if I were to build this power series or just write this power series out, we would have terms that would say 3 minus 3 over 2x plus 3 over 4x squared. And maybe we can think of the pattern, a couple pattern things that I notice. It's switching between negative and positive. So my next term would need to be negative. Each time the numerator was 3, but my denominator was a power of 2. So this first one was 2 to the first, matches the exponent. This one was 2 to the 0, which is just 1. 2 squared. So I'm guessing this one would be 2 to the third, or 8, with x to the third. And maybe my next one would be positive, and it would be 3 over 2 to the fourth, which is 16, x to the fourth. And then I could keep going. So I could look at this series that happens, 3, negative 3 halves, x plus 3 fourths x squared minus 3 eighths x cubed. And I notice several things. One, I know this is going to be a series that we're going to go from n equals 0 to infinity. It's alternating, and I want the first term to be positive, so negative 1 to the n. And then I'm going to look and see what else is happening. I notice that each time my numerator stays 3, so I'm just going to take a 3 out there. And then I see that I have an x to the n power over 2 to the n power. Oops, I don't like that. I'm going to go ahead and switch that. I'm going to put that n on the outside. So x to the n power and 2 to the n power. And then we're right back to where we started with the power series that we wrote before. So maybe this way takes a little bit more pattern recognition to try to figure out how these terms are related, whereas this one takes a little bit more algebraic manipulation to get it in to the right form. So you get to pick how we would do a geometric representation or a power series using a geometric representation. All right, let's look at one more. This one is a mess. This is not one I would expect you to be able to do on a test, nor would AP. But just let's look at what it looks like. Okay, the reason this one gets a little bit messier is because of several things. Do you notice that it says it's centered at x equals 2? That's going to play into our what needs to happen. So I'm trying to find a geometric power series. Remember, my goal is to get it to say 1 over 1 minus r. That's my goal. I'll write it down again just so we have it. My goal is something like 1 over 1 minus r. The tricky part is with this centered at 2 piece here, we have to take several things into account. One, this expression that is 4 over 2x minus 1 needs to actually say, instead of x, 2 times x minus 2. We need this x minus 2 here because this is what my center is. That's centered at x equals 2. So I need that there. Now the problem is, if I write that in, it almost looks like I've changed my problem. So instead of putting just a minus 1 here, I can't do that. I need the result of this 2 times x minus 2 plus whatever I choose to write here to actually equal 2x minus 1. So I know that if I add a plus 3 right here, 2 times x would be 2x minus 4 plus 3 would give me 2x minus 1. So these are equivalent. Okay, remember my goal is to get the 1 in the front, so it should be 1 over 1 minus r, and this is not quite there. So then what I would do is reorder the bottom. So this is equivalent to 3 plus 2 times x minus 2. Good so far? Okay. First problem, we know, obviously, is this 4. That 4 in the numerator can come out. But the next problem is where it gets messy, because I know I want it to say 1 minus r, and this currently says 3. So here we go. I'm going to pull out the 4. Okay, that part is easy. So I'm going to pull out the 4, and then I have 1 over Here's where it gets messy. I'm going to need to pull out a 3. So I want you just for a second to think about, this part will be easy. If I factor out a 3 from both of these terms, here and here, the first term would be 1. That's nice and easy. But this second term would be this weird fraction of 2/3 times x minus 2. Why? Because then I have factored out a 3. I can multiply the 3 back in and I get the same thing I just had. Okay, still not quite done because I want 1 minus r. We can see up here that I want this to say 1 minus r, and mine currently says plus. So let's change this. I'm going to go ahead and pull out the 3 to leave me with 1 over 1 minus, well, what am I subtracting? I'm subtracting a negative 2/3 times x minus 2. And now it looks like the right form. So now I'm going to take this information. I've got this crazy r. The r value that I have here is all of this. This is my r value. So I am going to start by saying that my function, which we originally had was 4 over 2x minus 1. And I know what you're thinking. Why on earth are we changing something that looks as simple as 4 over 2x minus 1 to something as crazy as this power series? Well, sometimes we need to make a polynomial to be able to do some operations on, and that's what a power series is we're rewriting it as a polynomial. So I know that this function is equal to, we had this 4/3 we pulled out, whether it's in front of the sigma or it's inside the sigma, doesn't really matter. And then I'm going to do r, which we said is this negative 2/3 x minus 2 to the n power. So remember, this is my r value. And now I have a power series representation. Well, like I said before, this could be cleaned up. This is perfectly acceptable, but this could be cleaned up because I see several things that are happening. One, the first thing I see is that there's a negative. So really, I could take this 4/3 times the sigma from n equals 0 to infinity, and I could write this as an alternating. And I have still, oops, I don't know what I just hit, a 2 over 3 to the n, and an x minus 2 to the n. So you might think this is the only answer, and this is a great answer. There are several other answers you could see, and they all go with properties of exponents. Everybody's favorite. I actually like this answer. I think this answer is a little bit more usable, but just so you could see another answer, and then we'll talk interval, because this one's important to look at the interval on. Another answer that this could be. Do you agree that 4 could be rewritten as, 2 squared? And we could write this as 3. So I've got this times negative 1 to the n over, I'm going to write this as 2 to the n over 3 to the n. You'll see why in just a second. X minus 2 to the n. You'll notice I left off the sigma, or maybe I just throw it in front of everything. Okay. Using properties of exponents. If I have a 2 squared and I have a 2 to the n, the bases are the same, so those exponents can be added. So this is the same as 2 to the n plus 2. And in the denominator, this is 3 to the first, and this is 3 to the n. So I could rewrite this as 3 to the n plus 1. So it's still alternating. It's times this multiplied by x minus 2 to the n. So I could go about it this way if I wanted to. It's the same answer. Not really necessary. Just another way to look at it. All right. We need to talk interval, though. And this is a great one because my interval will change just a little bit based on order of operation things. Okay. So first, I know that with a geometric series, my interval converges. Let's see if I can scoot this over just a little bit. Okay, so we have the interval, and I know that this has to be the absolute value of my r, so that negative 2/3 times x minus 2 needs to be less than 1. That's the absolute value of that. Order of operations for dealing with or simplifying absolute value and finding this interval. The first thing I'm going to do is I don't really need this negative sign right here because I'm taking the absolute value. So I'm just going to go ahead and get rid of that negative sign. And then what I'm going to do is I'm going to take and multiply everything by 3/2. So really what this says is that the absolute value of x minus 2 needs to be less than 3/2. Okay, if this is true, then I need to write a statement that says x minus 2 needs to be less than 3/2, but also greater than negative 3/2. And now I can add my 2. I can't add my 2 until I do that. So now I'm going to add my 2 to both sides. And if we add 2 to both sides, or all sides here, 2 is 4/2, so negative 3/2 plus 4/2 gives me 1/2 is less than x is less than 4/2 plus 3/2, which is 7/2. So my interval of convergence goes from 1/2 to 7/2. Couple things you should notice about that. Notice what number's right in the middle of this interval? 2. 2, my center, should be in the middle of my interval. And I should always make sure that that center converges. It should always converge at the center. It's just whether it goes beyond the center that we're looking at. Okay, so we've looked at pretty thoroughly how to find or how to take rational functions and write them as geometric power series. But now what we're going to go into is the idea of substitution. Remember those 3 series that we looked at on the first day we started talking about power series in 7.1? We found the 3 that say the sine of x is alternating odds, cosine of x is alternating evens, and e to the x is just x to the n over n factorial. We're going to use that to find other power series. And actually, this is going to make my life pretty nice to be able to do. When we start writing or making substitution into known power series, the first thing that we're going to do is start with the function that we know. We know f of x is the cosine of x squared. So what I'm going to do is I'm going to ignore this x squared for just a moment, and I'm going to think about what my function would look like of the power series without the x squared, and it would be the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial. You'll notice I left the x out, because what I'm going to do now is take what my argument is of my cosine. Since it's not the original argument, I'm going to take that x squared, and that's going to go in here. So this is going to become x squared. And it's as simple as that. I can clean it up. I can clean this up to say that this is going to be the series from n equals 0 to infinity of negative 1 to the n, x to the 4n over 2n factorial. So hit pause and try example 5 and see if you can get what this power series representation should be for e to the x squared. All right, for this function, what we should do is if f of x is equal to e to the x squared, again, my argument is this x squared, so it's a little bit different than just e to the x. So I'm going to have this series from n equals 0 to infinity of, instead of x to the n over n factorial, I'm now going to replace that x with the x squared that was there. And then I can clean this up if I need to. So we would have n equals 0 to infinity of x to the 2n over n factorial. And if I were to build out all those terms, I would see it's equivalent to the polynomial of e to the x squared. All right, I actually wish they were all that easy. Because the next thing that we're going to look at is what it takes if we need to differentiate or integrate a series to find a series that we want. Let's look at this first example. It specifically says to express f of x, which is 1 over 1 minus x squared, as a power series by differentiating 1 over 1 minus x, and find the radius of convergence. Okay, here we go. Okay, so I'm going to take this series that they told me to start with, this 1 over 1 minus x. Hopefully that looks a little familiar to you. Hopefully you notice that that's the geometric series. This rational function, 1 over 1 minus x, is the geometric series that is equivalent to the sum of, from n equals 0 to infinity, of x to the n. And if I look at all my terms, so if n is 0, x to the 0 is 1. If n is 1, we get x. If n is 2, we get x squared. If n is 3, we get x cubed, and so on. Do you agree with that statement? Okay. Watch what happens. I am now going to take the derivative of this expression right here. So if I take the derivative with respect to x of this expression of 1 over 1 minus x, can you think about what that derivative would look like? Okay, it might be easier to think about this derivative using negative exponents. Sorry, couldn't get my brain on. Of using negative exponents, this is really like saying 1 minus x to the negative 1. And if we take this derivative, we would get negative 1 times 1 minus x to the negative 2, but I would need to multiply by the chain. Multiplying by the chain would give me positive 1 over 1 minus x to the negative 2. Do you agree with that? Oops, sorry, it wouldn't be negative 2, it'd be positive 2. You shouldn't agree with that. Do you agree with that? That the derivative of 1 over 1 minus x is actually 1 over 1 minus x squared. Well, great. That's why they told me to differentiate this, because I can write a power series this way. Okay, going back up to the top, if I then take the derivative with respect to x of all of these terms, if I take the derivative of those terms, my first derivative would be 0. My next derivative would be 1. My next derivative 2x. My next derivative 3x squared, and so on. Do you agree with that? Okay, so if the derivative of this 1 over 1 minus x, which is equivalent to this series, and the derivative of this expression, which is also equivalent to that series, the derivative is 1 over 1 minus x squared, then doesn't it stand to reason that these terms should be 0, 1, 2x, 3x squared, plus, and we can keep going. Now, doesn't it also seem kind of silly that we write the 0 term? That seems weird. Why would we write this term? Why would we write this x equals 0? So I'm just going to go ahead and erase this 0 plus term and know that I want to start at 1. Well, that's going to change some things, right? Okay, so let's verify this. We took the derivative of 1 over 1 minus x, and we got 1 over 1 minus x quantity squared. We took the derivative of all the terms and got a set of terms. So doesn't it stand to reason that then I could also take the derivative of just the series itself, and it should be equivalent to both of those things? So really, this should be equivalent to the series from n equals 0, we're going to talk about that here in just a second, to infinity of, well, this is just a power rule. I have an x to the n, and if I take the derivative of that, it would be n times x to the n minus 1. Doesn't it stand to reason then that if I can take the derivative of this to get this expression, then the derivative of its power series is equivalent to that expression? meaning I just wrote a power series. And it should also equal all of these terms. But let's check that. Remember, we had that funny +0 that we erased, that we didn't really need to write a +0 because it's not adding anything to the problem. So if I think about taking this and plugging in 0, what would be my first term? Well, my first term would be 0 because 0 times anything. But does that actually help me any? Now, it certainly doesn't hurt me, but it doesn't actually help me. It doesn't provide any value to my series because plugging in 0 and getting 0 and adding 0 does nothing. So we would be better off shifting our index up to 1 so that my first term is what we call a non-trivial term, meaning it carries some weight. It matters. Because it's not just 0. We add 0, it doesn't really matter. So this would be my power series that represents 1 over 1 minus x squared. But now I need to find my radius of convergence. This doesn't ask for an interval, but I know I was representing, this is a geometric series. That 1 over 1 minus x is a geometric series. So if we look at our interval, we know that the interval of r, the absolute value of r, needs to be less than 1. Well, if the absolute value of r for the interval is less than 1, then I know my radius is in fact equal to 1. Why? Because my interval would have to go from -1 to 1, which means that the total distance is 2, so the radius is 1. So my radius here is 1. Okay, one other type. This one says we want to find a power series representation for the function f of x equals the natural log of 1 plus x and find the radius of convergence. You'll notice I didn't tell you what you needed to do with this one. So I want you to think about what we already know. Are there any power series that we know for sure? I'm going to tell you it has to do with the geometric. Think about this for just a moment. What is the relationship between the function 1 over 1 plus x and my function, natural log of 1 plus x? Is there a relationship between this function and this function? Hopefully, what you think about is that the derivative of the natural log of 1 plus x is 1 over 1 plus x. So do you agree? Is it fair to say that f prime of x is equal to 1 over 1 plus x? Is that a true statement? Okay. Well, if that's a true statement, what form do you notice this is really close to? This is really close to that geometric form that we looked at in example 1, right? So instead of being 1 over 1 plus x, we're going to rewrite it to fit that form of 1 over 1 minus r, where this becomes my r value. And so this would be the series from 0 to infinity of r, which is negative x to the n power. Do we feel good with that? Now, just like before, if this is my f prime of x, then this also is my f prime of x. So if f prime of x is equal to this series from n equals 0 to infinity of negative x to the n, then if I want to find f of x, what I need to do is take the integral of both sides to find what f of x would be as a power series. So I need to take the integral of the series from n equals 0 to infinity of negative x to the n power. Great. Okay, let's think about what we know and what might make our job just a little bit easier on this particular problem is instead of looking at it as the integral from n equals 0 to infinity, I'm going to change it to an alternating series, and I'm going to pull that negative 1 to the n out. So I have negative 1 to the n, x to the n. Why might I do that? Well, I'm taking the integral with respect to x. That means everything with an n, you guys, is just a constant. So this is just a power rule. For a moment, ignore this negative 1 to the n. Let's just pretend it's not there. Wouldn't I, if I were taking the integral for x to the n, I would go up a degree and divide by that degree? Do you agree that's the integral of x to the n? Well, the negative 1 to the n is just a constant. And so this power series becomes the series from n equals 0 to infinity of the alternating part, negative 1 to the n, x to the n plus 1 over n plus 1, and I can't forget my plus c. Now, sometimes we shift the index up just to make the function look a little bit prettier. It is possible to rewrite, just like we did before, it is possible to rewrite this series. If I'm going to shift my series up from n equals 0 to n equals 1, I could rewrite this instead of x to the n plus 1, I could do n, just n, but then this term would need to go down, and this could go down as well. So this would be an alternate form that would say the same thing. Now, I need to find a c value. I need to find a c value for this power series representation. So to do that, to find c, what I'm going to do is I'm going to let x be 0. And it doesn't really matter which function we go into, but I'm going to start with this f of 0. If x is 0, then the natural log of 1 plus 0 is equal to 0. Well, that helps quite a bit because if x is 0, I can use that, and y is 0, I can use that to find c. What that would say is that I'm going to take the series from n equals 0 to infinity of negative 1 to the n, 0 to the n plus 1 over n plus 1 plus c, and this whole expression needs to be 0. Okay, well, what does that mean? It means that I really have 0 plus c needs to be 0, which means in this case c is 0. Not very exciting, but if we know what c is, I can write my power series. And so I can say that the natural log of 1 plus x, which is my function f of x, is equal to the series from n equals 1 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1. And maybe I use this other series. Maybe I use this one that was here in the lighter gray, and I write it here. That would say the same thing. That's fine. Now, this is still a geometric power series. We know this is a geometric power series because I have negative x to the n, which means that my interval of convergence would be the absolute value of r, which is negative x, needs to be less than 1, which means that my radius of convergence would be 1. Okay, something you should know. Whether I'm taking derivatives or antiderivatives here or here, my radius and my interval of convergence will be preserved. So that radius of convergence is preserved regardless of what I'm doing, derivative work or not. So I will say this is the weirdest section we've got, dealing with writing something in power series. You have an assignment that goes not with this, but with the calculus of power series. So we're going to take these ideas and combine it with 7-4 and put the assignment in one thing. So hopefully that'll make a little bit more sense when we start to look at the calculus of it. This was really just trying to get a function into a power series form. All right, you guys, feel free to rewatch, pause, rewind, fast forward, whatever you'd like to do if you need to see some of this again, if there was a concept you didn't fully understand. Otherwise, let's continue on with the calculus and then see how we can answer or deal with some of the questions that are going to be given to us. Have a great day.